This publication is from Scientific Reports. The basic idea in this research article is these researchers have extracted a compound from the cannabis plant that is related to THC but has a higher activity in animals than THC. As usual, let's go over some background information. This compound is THC, or delta-9 tetrahydrocannabinol. It's the most well-known cannabinoid, as is the compound in marijuana that is associated with producing intoxication. Its main key feature that differentiates itself from other types of cannabinoids related to THC is it has this 5-carbon chain attached to it. This next compound is known as THCV. The main feature of this compound is that it has a 3-carbon chain, and it has been reported in previous literature that 3 carbons are necessary to activate CB1. For example, if you had a 2-carbon chain at this position, this would not produce an intoxicating-like effect because it wouldn't activate the cannabinoid type 1 receptor. This next compound is known as THCB. This research group also isolated this compound in previous literature. Its key feature is that it has a 4-carbon chain. And finally, this last compound, called THCP, its key feature is that it has a 7-carbon chain. We'll see that the researchers in this publication end up pulling or extracting this compound out of the cannabis plant and showing that it has higher activity in animals than THC. In this first test of the publication, the researchers have isolated and characterized both CBDP and THCP. In panel B, the researchers have used a process called high-pressure liquid chromatography, or HPLC for short. The basic idea is that you can take a mixture that is not pure, put it through something called an HPLC column, heat it up, and the compounds will come off at different time points because of their chemical characteristics. We can see that CBDP came off the column at 19.37 minutes, whereas THCP came off the column at 21.29 minutes. Panel D is something called a mass spectrometer. Mass spectrometry takes your compound and breaks it into fragments based on its molecular weight. What they're trying to show is that both natural and synthesized THCP show the same chromatogram on a mass spectrometry readout, and this 343.2628 is the molecular weight of THCP. And they are also showing the relative abundance. So they're just trying to show, once again, in very simple terms, that because the molecular weight of THCP is 341.2483, then that must be the right compound. And natural and synthesized show the same unique fingerprint. Now, in my opinion, this is the most interesting part of the research article, because it's where they actually measure THCP's activity in mice. They use something called the Tetrad test, or Tetrad effects. How this works is you first measure the animal's body temperature. You then inject it at 0 time point with the drug THCP. At 30 minutes, you run something called an open field test, where you just let an animal run around for a set period of time and track its movements. You then measure the animal's body temperature, see if it goes up or down. You then perform something called a bar test to measure a possibility that the animal is in a trance-like state. What you do is you force the animal to go on its front paws and kind of stand up and put its paws on a circular bar. A normal animal that is not intoxicated will take its paws off basically right away, but a very stoned or intoxicated animal will leave its paws on for a very long time. You then perform something called a hot plate test at 85 minutes to test how much pain the animal is currently in. In panel B, we see the first assay, which was the open field test. Notice how the control animal runs around a lot. If you look at panel C to correlate this with the distance, this is about 7,000 centimeters that the animal is covering. At a dose of 10 milligrams per kilogram, notice how little the animal is moving. And if we correlate that in panel C to the amount of centimeters moved, it is about 200, drastically less. Now at 5 mg per kg, the effect is the strongest, as the animal has barely moved at all, and this is correlated with about 180 centimeters of movement. I have put an orange line under this to indicate wherever the maximal effect is occurring, and it is occurring at 5 mg per kg. We see at 2.5 mg per kg, the effect is not as strong, but it is prevalent as the animal has moved about 4,000 centimeters. The next test was hypothermia. We said the control animal would have its body temperature measured before being injected with the drug, and it has a normal baseline physiological temperature of about 37 degrees Celsius. We see at 10 milligrams per kilogram, the body temperature of the animal has been suppressed or is about 7 degrees lower. That is a lot. With THC, you normally see an animal's body temperature at this dose drop by about 3 or 4 degrees Celsius. And this is the maximal effect at 10 milligrams per kilogram. At 5 mg per kg, we also see the effect, but it's a bit less than 10, and at 2.5, it's even less. But it does cause the animals to drop in body temperature. Now the next test, catalepsy. We said this was a measurement of a trance-like state that the animal was in. It is conducted by putting its front paws onto a circular ring and seeing how long it takes the animal to move. The control animal takes its paws off right away. The animal injected with 10 mg per kg takes a very long time to pull its paws away, at about 500 seconds. That is a very strong response. And at 5 milligrams per kilogram, we see the maximal effect of the drug. At 2.5, the effect is still very prevalent. The last test is the hot plate test. You basically put an animal on a plate that is fairly hot, not going to kill the animal, but it is pretty uncomfortable, and we'll notice the control animal stays on the hot plate for about 20 seconds. At a dose of 10 mg per kg, we see the maximal effect as the animal stays on the plate for about 60 seconds, indicating that it's experiencing less pain due to the THCP. At 5 mg per kg, the effect is still very strong, but not as strong as 10. And at 2.5, the effect is strong, but drops off a bit. The next parameter measured in this publication is one I've talked about before. It's called binding affinity, and it basically measures how tightly a drug interacts with a receptor. The lower the value, or closer to 0, the stronger the drug will be sitting inside of the receptor. Let's first take a look at panel A. We'll notice we see a drug, and we see an R group, propyl, butyl, pentyl, and heptyl. What we see is that going from propyl to butyl, if you look at the CB1 receptor, the affinity goes from 75.4 to 15 nanomolar. This is a drastic increase in affinity. But once we put a pentyl chain on there, the affinity goes up to 40, indicating that the affinity is getting worse when we go from butyl to pentyl. But when we go from pentyl to heptyl, going from a 5-carbon chain to a 7-carbon chain, we see that the affinity goes from 40 to 1.2. That is a large magnitude increase in binding affinity. In fact, it is 33 times more active than THC in terms of binding affinity. In panel B, they're just trying to show that when they run binding affinity, they have to use a radioligand for this experiment. The radioligand used is CP55940. This drug is a really strong agonist at CB1 receptor. It was made illegal many years back because people were getting high on it and supposedly running around naked in the streets or going insane. It was one of the compounds in that synthetic marijuana called spice. So what they're trying to show here is that we go from 6 to 7 to 8 to 9 to 10, we see this drop off. And the drop off is because the way the assay is run, they first attach the CP55940 to the receptor, and then after that, they take increasing concentrations of THCP, the experimental compound, and put it in the assay. And as the concentration increases, we can see the effect drops off because we are kicking more and more CP55940 out of the receptor. In this next part of the publication, the researchers took THCP and used molecular modeling software to bind it to the orthosteric pocket of the CB1 receptor. Panel C is showing THCP in blue and all of the interacting amino acid residues that would interact with THCP inside of that orthosteric pocket. In picture D, this is a little bit better of an understanding of what's going on, I think at least. We see this main hydrophobic pocket where the core structure of THC is going to interact with. The more important part of this binding is this yellow part labeled long hydrophobic channel. This is where things that are going to hate water are going to bind inside of the receptor. Long alkyl chains also hate water, so they will want to bind inside of this pocket of the receptor. And as you can see, if you put another methyl on the end of that 7th carbon, you would probably run out of room inside of the receptor. And it has been reported that if you put an 8th carbon on here, the effect goes down, or the activity of the drug drops off. But I often wonder if you took a methyl group and put it on the 1 or 2 position of the 7-carbon alkyl chain, that might actually help the effect of the drug because there is room inside the orthosteric pocket. This type of drug would probably not exist in cannabis, and somebody would have to make it inside of a lab as a synthetic cannabinoid. And in summary, here are the key points from this publication. THCP displays stronger tetrad effects in animals than THC. THCP's 7-carbon chain is the maximum chain length that can fit inside the CB1 receptor. THCP can be isolated from cannabis, although it was noted in the paper that the concentration of THCP in cannabis is very low. THCP has a much stronger binding affinity at the cannabinoid type 1 receptor than THC.